So far, we have looked at isothermal processes where delta T equals 0, constant temperature, and the internal energy is 0, such that our heat is now equal to the negative of the work done. And we have also looked at isochoric processes, and delta V for isochoric processes constant volume, so W is equal to 0, and the internal energy is equal to the heat supplied, using the first law of thermodynamics for a closed system. Isobaric processes, that's processes at constant P, and then we arrive at Qp equals the change in enthalpy of the system. In this video, we will be talking about adiabatic processes. In adiabatic process, there's no exchange of heat between the system and the surrounding, that is Q equals to 0. So what that means is that from first law, the change in internal energy is equal to the work done by the system or on the system, total work done. So an adiabatic system is such that it's insulated from the surrounding. It's like almost an ideal system. So we have the symbol delta U equals work adiabatic. Now we will derive the relationship between the state variables in an adiabatic process. Okay, so we recall that the change in internal energy is the molar heat capacity at constant volume times change in temperature, and that work is minus P dV. So in an adiabatic process, that's a process that takes place adiabatically, where all the internal energy is used to do work, Cv dt is equal to P dV. So this will be dV. So if we consider what P is RT over V. We're considering it for 1 mole now, and put it in the equation. So we have Cv dt equals minus RT over V dV. So rearranging the equation to put like terms together, T comes to this side of the equation, and then we have Cv dt over T equals minus R dV over V. Minus R dV over V. So, if Cv is independent of temperature, we can integrate from stage 1 to stage 2. If Cv is independent of temperature, it can come out of the integral. R is a constant, it can also come out of the integral. We have the laws of integration. 1 over x, integral of 1 over x is ln x. So using that, we have that Cv ln T2 over T1 equals minus R ln V2 over V1. So with some mathematical manipulations, we divide through by Cv, and then we arrive at ln T2 over T1 is minus R Cv ln V2 over V1. Applying the laws of indices, we can bring R over Cv to this side. So that would be ln V2 over V1 minus R over Cv, or taking out the negative sign, ln V1. So this is now exchanged now. The indices over here are exchanged. So we have ln V1 over V2 raised to power R over Cv. We recall that Cp minus Cv is R. That's from the video on heat capacity. So this gives us ln T2 equals ln V1 over V2 R over Cv, and that's equal to ln V1 over V2 Cp minus Cv over Cv. So this is now gamma minus 1, where gamma is Cp over Cv. So this is now Cp over Cv minus Cv over Cv. So Cp over Cv is gamma. It's called adiabatic index. and CV over CV is 1. So we're taking antilogarithms. We have that T2 over T1 is V1 over V2. So in an adiabatic process, we have that our T1, we are going from stage 1 to stage 2. So T1 V1 raised to power gamma minus 1 equals T2 V2 raised to power gamma minus 1. So all these equations apply to ideal gases. In a similar way, we can derive relationship between temperature and pressure, and also pressure and volume. One thing to note, so like this, so P1 V1 raised to power gamma equals P2 V2 raised to power gamma. And the relationship between temperature and pressure, T raised to power gamma, P raised to power 1 minus gamma, is a constant. The major difference, so the work done in an adiabatic process is CV dt, and if we have for n moles, we have n CV dt. The major thing about adiabatic processes as compared to isothermal process is that adiabatic process is always associated, sorry about that, with a fall in temperature. So we have an isothermal process that takes place, another isothermal process, so there's always a fall in temperature. The adiabatic expansion is associated with a fall in temperature, which tends to diminish the volume of the system, but the constant temperature, the temperature is constant in an isothermal process, so therefore less work is done always in an adiabatic process. Okay, so that's that about adiabatic process. A quick example. Calculate the adiabatic reversible expansion of 0.02 mole of argon initially at 25 degrees centigrade from 0.5 dm cube to 1.0 dm cube. The molar heat capacity of argon at that volume is this. Calculate the final temperature and work done. Gamma is 1.501. So if we bring out everything, the number of moles is 0.02, T1 25 degrees, V1 0.5, V2 1.0. The molar heat capacity is also given, and gamma. So for an adiabatic process, we can simply put it into the equation, make T2 the subject of the formula, and then we arrive at our final temperature. Work done. So T2 over T, so this is the final temperature, 66 Kelvin, 66.4 Kelvin. That's a big temperature jump. So the work done in an adiabatic process is, not ID, is W NCV dt, which is NCV T2 minus T1. So we have 0.002 times 12.48 minus into 2298 minus 66, so we have 57.8 kilojoules.